Welcome to the workshop. Today we want to take a look at section 3.3, continuous random variables. Now, the idea of a random variable isn't changing at all from what we saw in section 3.1 or 3.2. It's still just a function which assigns to the outcomes in a sample space a real number. That's all that a random variable is. Now in section 3.2, we considered discrete random variables where the possible values of the random variable were a discrete set. And here what we're looking at is we're having the possible values of the random variable being continuous. That's the only difference. And typically that comes about by the sample space itself being a continuous space. So those are the differences. We started off with a discrete sample space, which led to a discrete random variable. And here we're looking at a continuous sample space, which is leading to a continuous random variable. Now, it actually works out that we could have mixed random variables as well. And you'll find that the textbook highlights this in section 3.4, I believe. So let's just take a brief look at a continuous random variable. Essentially what we've said so far is probably sufficient for the section actually, but let's take a look at a couple of examples. All right, looking at our notes here. All right, so looking at our notes, let's consider the example of filling a car up with gas. Now I drive a Chrysler 200, which has about a 16-gallon tank, not exactly, but for numbers and easiness here, we'll say 16 gallons. And let's say I need to fill it up, right? How much gas is it going to take to fill it up? So my experiment is fill the car up with gas. The possible outcomes are I filled it up with 8.8 gallons of gas, 13.2 gallons of gas. And if I left it rounded to the nearest tenth, then I would actually have a discrete sample space. But if I could measure the exact amount of fuel that was put into the gas tank, then I would have a continuous sample space because I can put in between 0 and 16 gallons of gas. And so that makes sense. I can measure amounts, volumes. I can consider that a continuous variable. So excellent. If we take that idea, we can say, let's let our random variable be the function that simply takes on the value of the amount of fuel that I put in. So my sample space is, or my possible values, my sample space is 0 to 16, but that's also exactly what the random variable is, right? Those are the possible values of the random variable because it's just going to take on that particular value of the outcome. So there's little distinction between the sample space and the random variable itself. All right. So let's create a probability measure that is uniform for this. Of course, if we think back to the definition of a random variable, we need to have a sample space with a probability measure defined on that sample space. And then we can assign a function, and that's our random variable. So here we have a sample space, and we actually have a function, but we don't actually know that we have a probability measure defined on it. So that's what we need to define here. So we're not actually defining the random variable by any means. That has already been identified. The random variable is just taking on the value of the amount of gas that we put into the car. What we need to make sure that works here is the probability measure. So we need to find something that's going to satisfy the three postulates of probability. So let's take a look at how we can do that. I'll type this so we can read it here. The probability of a fill-up requiring between. So I'm defining our probability measure here. So I'm going to say, let's say we need to fill up between A and B gallons of gas. So between A and B gallons. So what's the probability of requiring that? So between 3 and 4 gallons, between 10 and 15 gallons, that sort of thing. So what's the probability that's going to have to be between A and B? Well, we're going to say that that is A, B, and B gallons of gas is, let's say it's b minus a divided by 16. All right, so this is our definition for the probability. We need to make sure that this agrees with or satisfies the three postulates that are required for a probability measure. So we're going to make note of that. Note that this does satisfy the postulates for a probability measure. So let's work through those a moment. What are those postulates? Well, the first postulate is that all of the probabilities are greater than 0. So for a less than or equal to b, because if we want between a and b, between 3 and 5, between 6 and 10, or whatever, right? We're not going to say between 6 and 2 gallons. We would say it in ascending order. So let's use that idea. So we have a is less than or equal to b. For a less than or equal to b, of course, if I were to subtract a from both sides, I would get 0 is less than or equal to b minus a. So we can say that b minus a is greater than or equal to 0. And of course, if I take that number and divide it by 16, I'll still have something that's greater than 0. That is, all probabilities are positive, or non-negative, rather. All probabilities are non-negative, which is exactly what we need. Excellent, so that's the first postulate. The second postulate is that the probability of the sample space is exactly 1. So the probability of the entire sample space is the probability that between, well, the entire sample space is between 0 and 16 gallons. So the probability of this is the probability that between 0 and 16 gallons of gas will be required. And we have a definition for that, right? Which has probability of 16 minus 0 divided by 16. Of course, that's 16 divided by 16, which is 1. That is, the probability of the entire sample space is exactly 1, which is what we needed. Excellent. So then we just need to show that the third postulate is also satisfied, and that's the probability of mutually exclusive events can be found by adding the probabilities of the two events. So the probability. So what would it look like to have two mutually exclusive events here? Well, let's say between 3 and 5 gallons are needed and between 10 and 12 gallons are needed. Those intervals don't overlap. So those would be mutually exclusive events. So the probability of requiring between A and B or C and D gallons of gas is, so if the idea is that we're just taking the length of the interval and dividing it by the total, or the length of, or the distance between 16, or between the gallons of gas, how many gallons range is there, we can just take the two numbers to get a total for the overall width of our interval that we're considering here. So between A and B or C and D is, let's see here, I want A less than or equal to B, less than or equal to C, less than or equal to D for convenience here. And we would find that it's B minus A plus D minus C divided by 16. So that's the probability overall. But of course, I could just consider these added together individually, B minus A over 16 plus D minus C over 16. And it's worth noting that this extends to any number of non-overlapping intervals. So that is postulate 3 is satisfied as well, because I can take the one probability here is the sum of the individual probabilities, which is exactly what we needed to show. So the 3 postulates are satisfied, and we have what we can call a uniform probability measure. And the reason that we call it uniform is because if I were to consider an interval of 1 gallon of gas, consider it between 0 and 1. Okay, compare that to the interval from 10 to 11. Those 2 intervals are going to have the same probability. So it's the same probability everywhere that we're looking at. Okay, is the idea. Hence uniform. All right. So that's all that I wanted to share for this video. We'll actually revisit this same example for looking at a probability measure that kind of agrees with the idea that I don't fill it up when I only need 1 or 2 gallons of gas. I fill it up when I need 10 to 16 gallons of gas. Okay, so that's the idea there. So I'll see you guys back in the workshop to continue this example very shortly.